Please be seated. Thank you. You know what I was thinking in the morning? This is the Computer Science Museum. And guess what? There is not a single quantum computer on display here. I guess what we should do is try to move this industry so that in 10 years from now, there are a number of them in the Computer History Museum. That would be really good. We need to have that kind of a momentum in the development. And in 10 years, I think it's doable. 30 years ago, when I was a postdoc here in California, at that time at UCSC, University of California in Santa Cruz, where I was, we just started the new disciplines, computational physics, computational chemistry, computational medical sciences, and so on. We're all very new. There aren't anymore, that's for sure. However, quantum computational physics and quantum computational chemistry and quantum computational medicine are quite new, arguably. And this is what we are going to talk about in this panel. The panel is about applications. So we do not concentrate on hardware and software. We like to discuss what kind of applications are possible and what the needs are for those applications. On the panel with me, Jamie Cohen. She is the R&D Director in Corporate R&D at Dow Chemical Company. Next to her, we have Daryl Nazareth. He is a medical physicist in Roswell Park Cancer Institute. And then Jonathan Carter, Deputy Director for Computing Sciences, Lawrence Berkeley National Lab. They will take turns now and describe what they do and how they use quantum computing for their work. Jamie, please.
Thank you very much. Can you all hear me? We're right after lunch, so let me take a clicker here and get started. Does it matter which one?
You're good.
Okay. So, it's a pleasure to be here speaking to you because I am not a computer scientist. I am also not a quantum computing expert. I am just a chemist, apparently. But I think that very soon you guys are going to find that we are your best friends. Or we're going to have to work in that way because we have some very challenging problems to solve in the field of chemistry. And the Dow Chemical Company has a very broad range of challenges that we face every day trying to solve. And well, I don't know where Andrew Fersman is, but yes, there are people in labs doing exactly what he showed in that picture every day, probably with much nicer equipment and maybe more chic lab goggles. But we have people at the bench working to try and just brute force synthesize molecules and materials in order to solve problems to make money. That's also my role. So let's get started here. I want to talk to you a little bit about the Dow Chemical Company because I want to impress upon you the size of our organization and the breadth of problems that research and development solves there. I'm in research, but I'm also in something called central research. Central research allows us to see problems across the company and feed solutions into different business R&D sectors. So we have a number of technology platforms in the new manifestation of the Dow Chemical Company. We work on everything from plastics to paints to silicone-containing materials. Well, what does that mean? It means that we have a variety of size scales and length scales that we have to deal with. We're synthesizing molecules in order to impart something performance-wise on a material for a particular application that has to do certain things, right? Has to be tough, has to be transparent, has to be rigid or robust. All of those problems have to be solved by synthesizing new materials. And we do our research using a variety of tools. I have 3 jobs that I have to do as an R&D director: find talent, develop tools, and deliver technology. And so we do this by using a lot of world-class capabilities. We use, at the top of this list, high throughput research. Well, what does that mean? In one manifestation, it could just mean I'm going to dump a whole bunch of stuff into a robot and I'm going to have it crank out thousands of experiments and I'm going to hope that something hits. But hope is not a strategy, and again, I have to find unique ways to accelerate innovation in order to deliver novel solutions to our customers, which are the businesses in Dow, as well as to our customers' customers. So, how do we do this? How do we use high throughput in combination with process engineering, high performance computer modeling, and application development to accelerate innovation? One of the ways that we do this, and I think it's important for you all to understand kind of your user base. We don't really have a desire to bring in a quantum computer or program this ourselves. That's why we're partnering currently with 1QBit, but in general, partnering because we want to use this new technology space. We're users. We need an interface that's going to fit into our workflow of how we do research in order to move things forward. So corporate R&D is a great example. We are a hub for developing new tools, and that's why in my organization, we focus on organics, polymers, and organometallics. We synthesize molecules, but we have a lot of other organizations within our corporate R&D. It is a subject matter expertise technology center for analytical sciences, material sciences, and others. And you can imagine the breadth of problems now, the size scales, the length scales, and how we have to put together a workflow in order to make this happen. Computational chemistry today is part of that workflow, and that's where we're going to think about integrating quantum computing. I've already talked with you that we need to accelerate innovation, and I can do that in a couple of ways, right? I can throw a lot of organic synthetic chemists in a lab and use high throughput, but I can also start to really understand why my materials work the way they do. So I think that where we're looking for quantum chemistry or quantum computing is really helping us design materials right now, understand the structure function. Perhaps in time, we'll be able to use this to feed our high throughput capabilities to help us choose better experiments to do in the near term. But I think right now, we want to say these are the things that work really well. It's a molecule, it's a catalyst, it's an additive. We know it works. We know in what environment it works. And so can we start to understand more about the structure function properties? But that's a hard problem. When you talk about potential energy surfaces or the energy of a system, or if you talk about the conformation of a molecule in its transition state as it's going through its catalyst process, these are not problems that can be solved today with classical computing. These scale very differently. If I am looking at the number of conformations that a molecule has with 40 or 50 atoms, that's going to take a long time for me to find the lowest energy conformer, and it's not good enough for me to find the lowest energy. I need to know what that energy is, because I'm going to have a lot of other molecules that I'm interested in. So the question we're trying to understand is how can we incorporate quantum computing approaches to accelerate structure function discovery and research, and I think there's going to be stepping stones along the way with which we can do that.
Thank you very much. Jonathan, it's your turn. Thank you.
Can everyone, yes, I guess everyone can hear me. Hi, I'm Jonathan Carter. I'm going to tell you a little bit about Berkeley Lab, its involvement in quantum computing, what we've started to do and what we hope to do in the next 5 to 10 years. Berkeley Lab is shown, it's within this white outline here. It's just in the hills just above UC Berkeley campus. It's run by the University of California on behalf of the United States Department of Energy. The Department of Energy is interested in sponsoring pure and applied research for the energy security of the US and the world. So that really is what motivates most of the research problems that we face at the lab and how we deal with them. So the lab was founded by Ernest Lawrence, who's sitting on the bottom row here, and, roughly in the middle, in 1931. And Lawrence decided to get together this concept of a multidisciplinary lab because he couldn't do what he wanted to do within his role as professor of physics at UC Berkeley. So he got together a team of manufacturers, of physicists, of chemists, of engineers, and they're actually sitting here on the core of an electromagnet which will form his biggest cyclotron. So Lawrence won the Nobel Prize in the early 50s for developing the cyclotron, and he did it with this concept of big team science. So Berkeley Lab was the first national lab, and it's grown since then to be a 17-site complex. So kind of in a nutshell, 13 Nobel Prizes associated with the lab. It's about 4,000 employees, just short of $1 billion of funding a year. And as I said, it's operated by the University of California. So let me talk about computing sciences at Berkeley Lab. I've been involved in high-performance computing for about 30 years now. 20 of those years have been at Berkeley Lab. And so within our computing sciences family, we have two things which will strike you as well, three things really, but two for the moment as very traditional. We have a high-performance computing center, which will be very familiar with, I think, many of you. It's similar to those run by the National Science Foundation, run across the world, where scientists and engineers can come with very large problems and run them on state-of-the-art hardware, systems that might be in the top 500, the top 10 of the top 500, very large systems, things like that. And we have such a computing center at the lab, and it has about 6,000 users from all over the US and all over the world. We also run a networking facility that connects together all the DOE labs across the continental US. And that's very important because DOE users might not only use computing resources, they might also use physical facilities like an advanced light source, where you can get ultra-high collimated X-ray beams to do probes of molecules or surfaces or things like that. And you want to be able to move those data sets around from lab to lab to use the most appropriate tool for your data at that particular point in time. So the network is a key part of what we do at the lab, keeping everyone connected, as it were. And then we have a research and development organization with a very strong applied math and computer science programs. We're building up a data science program at the moment, and we have what we call science partnerships, where we get together people like myself, a chemist, together with applied mathematicians and computer scientists to tackle a problem all together. Maybe we need a new kind of programming language, maybe we need new math, maybe we need to think about chemistry another way. By bringing these communities together, we can get a much better science impact. So very recently, in fact, at the end of September, Berkeley Lab received 2 awards to conduct research in quantum computing. And this is the first funding that the DOE has actually put out there for quantum computing. It's maybe a little bit late in the game, but we really hope to catch up, because it's pretty obvious that a NERSC, that's our computing facility of the future, will possibly employ all kinds of special purpose hardware, as well as the large parallel systems we have at the moment. It could include quantum computers, it could include brain-inspired computing, but it's certainly going to be less homogeneous future going forwards. So we have 2 endeavors that I said have just started. The first we're calling the aqueous testbed, and this stands for Advanced Quantum-Enabled Simulation. And this is a collaboration with multiple divisions at the lab and also with UC Berkeley campus, particularly at the campus with Irfan Siddiqui's Quantum Nanoelectronics Lab, where they've been fabricating superconducting circuits now for quite a while. So there, the objective will be to bring together a group of physicists who already know about qubit construction, people at the lab who have been developing high-speed control electronics, and see if we can scale some of the hardware they have at the moment to a greater number of qubits, and also see what kinds of optimizations might be made for the particular DOE mission-relevant problems that we have in quantum computing. So to complement that effort, we have a quantum algorithms team, which is instantiated in the research division, which is primarily focused on chemistry, but we'll be trying to develop tools that will hopefully be useful to lots of other applications over the course of the project. And so one of the One of the focuses here is machine learning for chemistry, also linear algebra for quantum computers, which can be used for computational chemistry. And this morning, someone mentioned the famous HHL algorithm for quantum computers that promises exponential speed up. I think we're going to see lots more algorithms like that that will produce these speed ups for lots more problems. Okay, so let me talk a little bit about energy applications. After all, that's what the lab is about. And some of these, I think, are tightly tied to societal energy impacts, and some are a little bit less so. But I want to cover just a few of them. So we've had a lot of talk about this morning, and Jamie also mentioned it, discovering better materials for things like catalysts. And I think it's very important to remember that there's substantial energy gains that could be made by improving catalytic cycles. One of the ones that's often mentioned, and I think it's worth mentioning in this context here, is the process that's used to fix nitrogen. So nitrogen has a strong triple bond. It's hard to cleave that bond and make ammonia. You want to make ammonia so you can make fertilizers. The current process for doing that was invented in the early 1900s. Fritz Haber, he won the Nobel Prize for that. But that's an old process. It requires very high temperature, high pressure, and by some estimates, it takes between 1% and 2% of the entire world's energy is used to fix nitrogen via this process. So what gives us any idea that we might be able to do better? Well, in fact, I'm sure if you were to look out one of these windows, you'd see some plants that are doing it just fine at room temperature and pressure. And the key to there is the nitrogenase enzyme. We don't really understand very well how nitrogenase works. It has a dense manifold of electronic states that has yet to been really comprehensively modeled. And we really hope that near-term quantum computers, maybe to 50 to 100 imperfect qubits, might get us quite a bit closer to being able to model exactly how nitrogenase performs these actions. There are many other applications at the lab. There are studies of quantum phase transitions, spin liquid studies that might lead to more efficient magnets, or maybe magnets that don't include rare earth elements, will be key components of better, more economical motors and things like that. There are many problems in the biological sciences. At the moment, we have one study looking at precision agriculture, whereby we can sequence random plants in a field. We can look at what bacteria are present, what particular strain of plant is there, and from that, hopefully decide the exact composition of fertilizer or nutrients or extra bacteria to feed it to maximize the yield in those fields. One really, I guess, kind of really forward-looking application would be if you look down here at the bottom left. This is a particle track that came from the Large Hadron Collider, which is the very largest collider at CERN, the device that was used to discover the Higgs boson. So at the moment, that's undergoing a refresh to increase the luminosity of the beams that will be collided. And when that upgrade is finished, the density of particle tracks that will be generated will really exceed the computational capabilities of the devices that are used to filter out the initial stream of data from that device and make it interpretable to the physicists. So we need to look for better computing technology that might be fitted in this device to enable these particle tracks to be decoded. So that's just a few of the many applications that we hope to get into with quantum computing. And as I said, the chemistry is the one that we're focusing on right now. And I'll leave it there. Thanks.
Daryl?
Good afternoon, everyone. And I'm really delighted to be here. I'm Daryl Nazareth. I'm a medical physicist in radiation medicine. And so a lot of my work involves clinical work. So for instance, if a patient's going to be treated with radiation, I'll check the plan to make sure the calculations are done right and the patient gets the right dose of radiation. So just to give some motivation and background, cancer is one of the leading causes of morbidity and mortality worldwide. In 2016, there were 8.2 million cancer-related deaths, and the number of new cases is estimated by the World Health Organization to increase by over 70% over the next 2 decades. Now, treatment of cancer is it's accomplished generally using surgery, chemotherapy, and radiation therapy. So as you can see here, we have a patient who's being treated using a linear accelerator, okay, or LINAC for short. And I have a couple little videos that just, if I can get it started. So maybe at the back they could play it. Okay, thank you.
Hit a small tungsten target where the electron energy is converted into photons, or X-rays. The high-energy photons emerge from the target in a variety of directions. The primary collimator only allows forward-traveling X-rays to pass through, creating a cone-shaped beam. The primary collimator minimizes leakage, and therefore excess total body dose, by absorbing scattered X-rays traveling in the lateral direction. It also defines the maximum size of the resulting clinical radiation beam.
Okay, so you can see there that we have a certain size of the field that we can define. And now the important thing is, how do we shape that field?
Radiation field. The X-ray beam is almost ready to treat the patient. Before that, further beam shaping is required to ensure that the shape of the delivered X-ray beam matches the shape of the tumor. This is done using a multi-leaf collimator, a number of fine tungsten leaves which move independently of one another and can create a variety of complex treatment shapes.
So you can see here that what's called the gantry will move around the patient, the shape of the field will change, and its intensity will change. And the idea is to deliver radiation to the tumor and to spare the critical structures, the sensitive organs, as much as possible. So the radiation dose can be calculated in the patient, and this is called absorbed dose, and it's calculated using well-known physics principles. Now, in order to optimize the dose to the patient, what we have is an objective function. Okay, so this is a typical objective function where we have one term that describes the dose that's being delivered to the target. Okay, the target is the tumor, and those are the cells where we want to deliver as much dose as possible in order to kill the cells. But of course, this is a trade-off because there are healthy organs involved too. And we could deliver enough dose to kill the tumor, but at the same time, if we don't spare the healthy cells, then we're not doing the patient any good. So this objective function is what needs to be optimized. In this case, W is a vector of the beamlet intensities and shapes. So you saw earlier that the linear accelerator defines different shapes at different angles. Those are the independent variables, and that's what we solve for when we do this optimization. So minimizing this function F results in the optimal treatment plan, and this has been an intense area of research in medical physics in the last 2 decades. So a few years ago, I started collaborating with the folks at D-Wave, and we used the D-Wave system to perform an optimization and to solve for the optimal beamlet intensities. And this was for something called IMRT, intensity modulated radiation therapy. So that's kind of a precursor to the kind of treatment that you saw earlier, where in this case it's a more simple type of treatment. The gantry remains fixed, and the leaves that you saw, those little finger-like devices, they move in and out of the field, but the field does not rotate around the patient. That's a simpler type of problem to solve, and that's how patients used to be treated. That's being replaced with the more dynamic treatment. And in this study, we applied it to the more easy, the simpler type of treatment, because the number of variables involved is smaller. Okay, so in conclusion here, quantum computing has shown promise in radiation treatment optimization, and further research on the application of quantum computing to VMAT, which is volumetric modulated arc therapy. That's the kind of therapy we see where the beam source is constantly moving around the patient. This may offer significant returns. Okay? And the improved treatment plan quality will definitely benefit patients. Okay, and I'd like to end with a small shout out to my mom in Toronto, because today is her 75th birthday. Thank you very much.
Settle in, Daryl. All right, let's see, a couple of quick questions. Jonathan, you volunteered and told us that you have 30 years in high-performance computing, but essentially 0 years in quantum computing. Is that a fair statement?
Well, hopefully not characterized as 0. So about 4 years ago, the lab director said, you need to think about what's going to come after CMOS. So think of a program. And at that point, I used some seed funding to start off a couple of projects in quantum computing. So I would say...
So it's more like 4 years.
Yeah,
Okay. How about you, Daryl? Computing in total, quantum computing in that bunch?
Computing has been about 10 years, and that's involved things like high throughput computing, where we collaborate with the supercomputer center, and we use it to optimize some of our treatment plans, just on a research basis. So the actual clinical work is done on individual workstations for the most part. But as far as the research part goes, we've been using the supercomputer approach for about 10 years.
10 years. Jamie, yourself?
Yeah, so Dow's been involved for a while using
you?
high-performance computing. I've only been at Dow for 10 years, and they've been doing high-performance computing for about 20 years, using it to solve a wide variety of challenges associated with kinetic modeling and systems modeling and process modeling. In my lab, we use computational chemistry, and that's also been for quite a while. We've only been endeavoring into this quantum space for about 8 months, and that's really all been with our partnership with 1QBit.
Do you feel a bit exotic in Dow doing quantum computing, or?
Yeah, I get a lot of emails. What is Dow doing in quantum computing? We're such a big company, and so you actually can imagine that there are other applications potentially for quantum computing outside of the chemistry space. But really, the focus is actually small, and there's a strategy there to understand it in my organization specifically.
Jonathan,
Berkeley, exotic? Are you guys exotic with your group, with the two groups?
It depends on who you talk to. For the physicists and chemists, not so much. For the applied mathematicians, still, in some cases, many think that Dan Leider's #1 Google hit is the truth. Quantum computing will not work. So.
And you, Daryl, do you feel as a pioneer of some sort?
In a way, I'd say, because even though my field has a lot of physicists in it, they focus more on the more traditional types of computing. And so the idea of using quantum computing is something that's very new.
And so suppose you had infinite resources and quantum was applicable to everything you do. What would you think it does achieve for you for your particular application, radiation science and stuff?
Well, if we could, say, improve the calculation throughput by many orders of magnitude, we could do things like what's called adaptive radiotherapy. So right now, the way the workflow goes is that the patient gets a CT scan done first, and then the treatment plan takes a few days. Then the patient comes back and then gets treated every day for several weeks on the linear accelerator. But what would be possible at some point with additional computational power is to have the patient on the treatment table, take a CT scan, and immediately perform the treatment plan optimization so that the patient can be treated immediately. And that way, if there's any change in the patient's anatomy, if the patient's lost weight, or if the tumor has shrunk during treatment, that could be taken into account dynamically. And so the patient would receive an improved treatment plan.
And in chemistry, Dow would be doing what exactly?
Well, I think what's really important to us in central research, but just in research in general, is to understand why our molecules or our catalysts perform the way they do, so that we can go off and make materials just like those. And so, as I talked about it, I think being able to tackle problems like solving the electronic Schrodinger equation for large molecules is going to be very important, but overlaying that too with the whole conformer problem of, these molecules have to interact in a pretty complicated environment. We have temperature, we have pressure, we have 10 to the 20 other molecules around it, and really understanding what the optimum structure, optimum transition state of those molecules is going to help us when we are in the lab, in the bench, trying to make that next best material. In general, I think it's almost impossible to think of the other applications that are going to occur in my field, because there's just so many cool problems to solve. I think even it was touched on in the last panel, AI, right? We have an opportunity as well to bring in some of those AI applications, but some of our problems are really not so much that we don't have enough data, but the data is very complex and it has a lot of signal to noise ratio issues, and we're gathering it from different labs across the world. And so anything that can make some of these problems more tractable by just thinking about them in completely different ways than we're tackling them to date, I think is going to be useful in the field of chemistry and industrial chemistry specifically.
Jonathan, you were mentioning some of the things you could do or you will do using these facilities. What kind of speed up are you looking for those in terms of orders of magnitude?
Well, for the chemistry and the materials applications, it's more a case of being able to do a problem that you previously really couldn't do. As Jamie said, you kind of run out of steam, depending on the method, maybe 50 or 60 electrons, and there's really no way to go beyond that if you want a fully correlated solution. So my hope is that quantum computers would enable us to go beyond that. So to do something really that we couldn't do before.
But do you have a notion of, well, I need 1,000,000 times the current available speeds, or just 10,000 times? Or what would be the rough order of magnitude? And I understand you do many different things. Just very roughly, take one and...
Well, I'll take the larger one then. Let's have 1,000,000.
1,000,000. Okay. Would 1,000,000 be good for you, Daryl?
Well, definitely. I mentioned the adaptive replanning, where the patient is on the table, the plan is calculated instantly based on the imaging that's done, and the patient can be treated. Every day the patient comes, the plan can be tweaked depending on how the anatomy has changed. But I think if you're talking about many orders of magnitude improvement, we can get into things like applying artificial intelligence to medicine. And that's not just in my field. I think in general, the medical field, one of the problems is a shortage of expertise, especially in underserved areas like developing countries, rural areas. And if we can basically mimic the best doctors, the best scientists, and use that expertise to be able to deliver services to these underserved areas, then that would really benefit patients all over the world.
Yeah, I'm asking this because I somehow have the feeling that we all hope that quantum computing will bring these orders of magnitude, which we don't actually know, infinitely faster, or just 1,000,000 times, or 100 billion times, or whatever. And I rarely see a discussion about it. What would be a sufficient speed up that would change my life or the life of my company? Do you have a notion for your activities?
No, I
Jamie?
think it really mimics what Jonathan was saying. Speed is great, right? And any little bit helps in terms of being able to maybe solve problems more quickly, or when we're looking at maybe combining classical with quantum, right? Speed will be great, but it's really, we're at a point where the problems are just intractable with classical. We can't do it. And so it doesn't matter if it's going to take me a week using quantum computing to do it. It's that I can actually do it. that is the important part.
So I noticed this morning that in the hardware section, there was, maybe in a natural way, but there was no mention of any hybrid models. That it was all rather fundamental. But the software panel was actually bringing up the topic of hybrid is actually interesting, and coprocessor. I have never thought I will hear that term again in my life. Coprocessor was mentioned, quantum coprocessor, and things like that. So how is it with what you are doing? Is hybrid a model? How would you combine it? What would be an access that you desire to be able to combine it?
Sure, I'm going to try and answer this question because when I put my chemistry hat on, I think about the molecules that we make, and let's just take a particular catalyst. And certainly the conformation or the behavior of these molecules is governed by all of the different atoms. But there's probably something very important in that molecule, maybe the active site, or maybe the main area that's going to be most important to govern the final properties of the system. And so I can imagine using a classical approach to understand this larger molecule approximately, but helping us to identify a particular piece of that molecule that we really need to dig into more to understand how it behaves, because that's the linchpin of driving the overall performance. So I think that there are ways that we can combine some of the approaches that we do today, and we are trying to continue to improve the classical approaches, as we've heard already, to help us narrow down kind of the size of the problem for now, until we have enough qubits to maybe tackle the whole problem in one big bite.
Daryl, is that the same for you? Can you live with hybrid?
Sure. There are aspects of these kinds of problems that I see that can be tackled with conventional computing. As I showed, we have the dose distribution in the patient, and that's calculated using well-known physics principles. And the gold standard for that, the gold standard algorithm, is Monte Carlo. It's not used as much yet clinically because it's still a very slow calculation framework. But that could be done, say, with GPUs or extra kinds of parallelization, just using a regular classical computer approach. So if we combine the Monte Carlo dose calculation with a quantum computing approach to do the optimization, then we could have both accurate dose calculation from the Monte Carlo, and we could have, say, we could find the global minimum of the objective function using the quantum annealing approach.
Jonathan, the projects that you got funding for are quantum computing projects. I suppose it's difficult to argue that I'm going to do that in a hybrid model then, or is that the case?
Well, no, I think near term, I think everyone will be really forced into a hybrid model. Several times this morning, people mentioned one of the algorithms developed for chemistry that tolerates imperfect qubits, and there's relatively few operations on them. That has substantial classical computing requirements to it as well. So I foresee the future, at least the next 5 years, will definitely be hybrid.
And so the easy thing with the hybrid is that there's enough skill everywhere, regardless whether it's a university or a research department or a company to develop those applications. However, quantum is different. There isn't that much skill available, and you cooperate with companies who help you. How much own skill do you have in your own organization to develop, write a quantum computing program or application, Daryl? What's your own?
I would say that we would leave that to the experts. So we would focus on the clinical physics aspect and have, say, maybe some kind of cloud-based service, something where we would send the data on the CT scan of the patient, along with the different anatomical information, like the tumor, the healthy structures around it, because that's pretty much how it's done now, except the calculations are done locally. But it's that information that's input into the system. So if we could send that, say, through the cloud, and then have the optimization performed using a quantum computing approach, they would send the information back on the solution, and then we could program that into the linear accelerator and treat the patients. That would be a good model.
Jamie, you did state that you are not really interested in doing it yourself at all.
Well, I mean, the field is still changing. We see this, right? It's moving very fast, and I think for Dow, we don't want to spend the time to try and move with the field in that way or try to lead the field. We want to spend our time developing those new materials, and so we want to leave it to the experts, as Daryl mentioned. But I think what's really important and what we've learned in our collaboration is bridging the nomenclature gap, basically, right? We have to be able to frame the problem in a way that somebody with the quantum computing expertise can understand. You know, why is it important? Why is it challenging? Why can't we do this today with classical computing? And so, you know, we have computational chemists. They have a strong chemistry background, but they also have a physics or a computational background, and that helps a lot. And I think as we move forward, I'm going to continue to hire that broader skill set of computational, chemistry, physics, and even some computer science, so that we can at least have that dialogue, and we know how to go back and start to articulate the problems that we want to solve. And then when they're describing to us those solutions, we actually know how to apply.
But that would have to be quantum computational expert now, not just computational expert. Those are available.
But I actually don't think that we need the quantum piece. I think that we need to still be framed in, you know, how things have been done thus far, so that we can start to say, hey, this is where we're running up against that wall. This is where you need to come in and to help us move that next step. I'm not sure that we're going to ever be looking for anything other than a functional communication ability within the quantum computing space.
John, that must be different for you. It must be.
Yeah. My experience at the lab is there's always people willing to jump in and try and learn about new conventional architectures, and I hope that is the case for quantum systems too. Initially, at least, we've tried to overcome the problem of not a lot of expertise in-house by partnering with organizations, universities, and other labs that have an existing base.
I tell you, while I'm asking these questions, because in my experience, back in the old days when computational physics and chemistry took off, that was the time when we actually started to have people who had both skills, could do the programming, deal with the systems, and did understand the physical or chemical nature of the problem at the same time. And I have it could be wrong, but I have the feeling that quantum application development will have to reach that level, that there are some people who can actually do it, but understand why are they doing it and what for are they doing it. Let's just make a quick test here. Please raise your hand if you think you could program any kind of quantum computer today. Oh, well, that's 3 of them. All right, in a specialized conference for quantum computing. So I think you understand my point. Something needs to happen. We cannot leave it like that. We can leave it to the experts, but there are not too many experts either. So, so something needs to happen here, and we need to invest. Now, our time is getting up, but let me then just do my last question. Each of you, what would you like to see in your professional life in terms of development of quantum computing, say on a long period of time before you retire? How did the world change, of your world change, because of introduction of quantum capability?
Yeah, I think it's somehow we've been able to integrate it into that workflow for innovation, to cut down on the number of cycles that it takes for us to find that next best material. Whether that's putting it in the front end, having a user interface that's going to be something that we don't need a quantum computer specialist to program, but somewhere where we can actually access it and integrate it more regularly into the entire workflow. It might be through the adoption of quantum computing within the AI space, but anything that I hope I'll see in my lifetime is anything that we can do to add tools to that innovation toolbox to reduce the number of reps that we have to do to find that next best material for taking it out to the world.
Daryl?
Well, I think if we can improve computation applied to other areas, like say genomics and maybe nanotechnology, then we can improve the kinds of treatment that we're administering to the patients in addition to the radiation therapy. And by combining these kinds of modalities, we can have more effective ways to treat cancer and possibly, within my lifetime, cure cancer. And once we do that, I will happily retire.
Jonathan?
I think it would be nice to see a computing center like NERSC, like many of the others, being able to offer a more universal quantum computing device. I think that's probably going to happen within
Going to happen
my
in your
career.
life. Yeah. Well, thank you. Let's take a few questions in the audience. If you'd like to ask a question, please raise your hand. There's one gentleman right in the middle.
So this morning we learned about different types of quantum computers, the computers that are better for solving optimization problems, and computers that are better for solving like universal problems. So in Daryl's case, it sounds like the problem you have in front of you is more of an optimization problem. But for the other two panelists, I'd like to know what percentage of your problems can be framed as an optimization problems versus universal problems. And if I may, my second question is, if you can have a quantum computer that can solve all the problems that you have, how much money can you ask for your boss to justify purchasing or using quantum computers?
Okay, then let's take the first one, and maybe all of you should briefly react to that. It's a very good question because of the whole discussion in the morning really showed that the real problems are actually, well, not real, every problem is a real problem once we ask it, but these application-oriented challenges are essentially, most of the time, reducible to an optimization problem. So please go take rounds. Jamie?
Yeah, I think we're still trying to understand that. I think that overall, to really do justice to the problems that we have, we're going to need universal. But I think we are making some progress with, again, using some of the annealer technology that we have today, along with the classical quantum hybrids. So again, we're still trying to frame some of the problems, and it's a great question of, both what are we going to need in the future to solve X, Y, and Z issues, but then also, maybe we can't solve the problem today that we're trying to frame, but are there other problems that are stepping stones along the way that are going to move the needle so that I can get more money from my boss?
And how much order of magnitude?
I was thinking about that, and I think it really depends on the problem that we're trying to accelerate. If I can accelerate the delivery of a new catalyst for some of our plastics applications, that can be valued in the billions of dollars, and so my boss might see that return on investment as pretty good. So it really depends on the final application.
Well, as the question asked, optimization is a big part of the medical physics problems. But there are other things too, like for instance, if we could have a system that could automatically segment the different types of tissue, the different types of organs in the CT scan, then that could provide more accurate treatment as well. So that might require something more like machine learning or something like a more universal type of quantum computing approach. As far as the money goes, I'm going to be much more modest than Jamie, and I would say maybe on the order of what a normal linear accelerator costs, which is in the several $5 to $10 million range.
Jonathan?
Oh, he wouldn't invest $1 billion. No. It has to be worth that for him to invest anything.
I think, like Jamie, we're still trying to assess what the balance of interest will be. Every time we hold a meeting or a briefing, different people emerge, excuse me, from the lab with different kinds of ideas about what they'd want to use a quantum computing for, so it's a little difficult to say. For the second question, so currently, you know, I basically have the numbers. We are spending about 3% of what is spent on the NERSC supercomputers on the test bed. I don't expect that total pie to grow, so maybe you know, quantum computing at the lab might be a $10 to $20 million a year effort tops.
One more question, if there is an immediate question in the audience. We are done, our time is up. Well, thank you very much. Let me wrap this up. Thank you. By thanking the panel and saying that I'm very upbeat about this now, because one can see that quantum computing is incredibly important, and I don't want to appear as a protagonist of the old world, but classical optimization, if done well, can go a long way here. And our digital annealer that gives you, you see the example, so the example of 15, 16, 17,000 times speed up is actually something that could help all of the panelists to do some exciting work before the quantum challenge comes upon us. Thank you very much. Thank you.